We've talked about Avogadro's law, which tells us that the moles and the volume of a gas are directly proportional. We talked a bit about what this means for our chemical equations and the coefficients. Our coefficients could represent ratios of molecules, moles, or volumes of gases in the reaction. In this example, we have one volume of nitrogen combining with 3 volumes of hydrogen to make 2 volumes of ammonia. Because the coefficients represent ratios of volumes, we can do stoichiometry problems based on Avogadro's law. We're just going to do it with liters instead of moles. In this example, we have propane gas reacting with oxygen gas to make carbon dioxide and water. This is a combustion reaction. We want to find what volume of oxygen gas at 25 degrees Celsius and 760 torr is needed to react with 2.7 liters of propane measured under the same conditions of temperature and pressure. It is going to be important for our stoichiometry type problems here that the conditions are the same. The temperature and pressure don't usually change, but if they do, that can affect the way you calculate the problem. That is why the conditions are listed in the problem even though they aren't explicitly used in the calculation. It's also going to be important for you to be able to pick out which information in a problem is relevant. In the real world, to solve a problem, you first need to know what information to collect. We're going to start with our value that we're trying to convert from, which is 2.7 liters of propane. We're going to use our coefficients from our balanced chemical equation, the same way we would for any other stoichiometry problem, except instead of writing moles, we're going to write liters. We are going from liters of propane to liters of oxygen. We have 1 in our balanced equation next to the propane and 5 in our equation next to the oxygen, so those values go next to liters in our stoichiometric factor. We do 2.7 times 5, and that gives us 13.5 liters of oxygen. Here's another stoichiometry problem with gases that we can do. This one's going to be a little bit trickier in a way because we're going to have to use the ideal gas law. The basic setup of this stoichiometry problem is actually the same as what we did in Chapter 7, in that we are going to use moles for our conversion. Here's the basic layout of the problem. We're going to go from mass of gallium to moles of gallium using the molar mass of gallium. We're going to go from moles of gallium to moles of hydrogen using the balanced chemical equation. Then we can go from moles of hydrogen to volume of hydrogen using the ideal gas law. That's really the new part of this problem. We start with the 8.88 grams of gallium that were given in the problem and convert it to moles by dividing by the molar mass of gallium, which is 69.723 grams per mole. Then we go from moles of gallium to moles of hydrogen using our coefficients. Moles of gallium goes on the bottom to cancel out, and it has a 2 next to it from the balanced chemical equation. Moles of hydrogen goes on the top, and there's a 3 next to it from the balanced chemical equation. We do 8.88 divided by 69.723 times 3 divided by 2, and that gives us 0.191 moles of hydrogen. Here's the new part of this. We're going to use the ideal gas law to solve for volume. We need our units to all match up. The temperature is given to us as 27 degrees Celsius, so we add 273.15 and get 300.15 Kelvin. The pressure is given to us as 723 torr, but it needs to be in atmospheres to match our R value. We take our 723 and divide by 760, which gives us 0.9513 atmospheres. We rearrange the ideal gas equation to get V by itself on one side of the equal sign and end up with V equals nRT divided by P. Once we have everything in the correct units that match our units for R, then we plug in our values and do our calculation. We just solved for moles of hydrogen and came out with 0.191 moles. The value for R that we're using is 0.08206 liters atmospheres per mole Kelvin, which were given in the problem. P is 300.15 Kelvin, and P is 0.9513 atmospheres. We come out with 4.95 liters. What volume of carbon dioxide, measured at 745 torr and 25.0 degrees Celsius, can be produced by the fermentation of 10.0 grams of glucose, C6H12O6, with a molar mass of 180.156 grams per mole? R equals 0.08206 liters atmospheres per mole Kelvin, and 1 atmosphere equals 760 torr. C6H12O6 aqueous reacts to yield 2 C2H5OH aqueous and 2 CO2 gas. Is it A, 4.16 liters, B, 1.39 liters, C, 2.77 liters, or D, 5.54 liters? The correct answer is C, 2.77 liters. You change grams of glucose into moles of glucose using the molar mass given in the problem, and then moles of glucose into moles of CO2. Once you have the moles of CO2, you can plug that value in as N in a rearranged form of the ideal gas law. The pressure needs to be in atmospheres in order to match up with the given units of R. So you'll take your 745 and divide by 760. Temperature has to be in Kelvin, so you'll add your 25 plus 273.15. When you plug in the values with the correct units, you can solve for volume of carbon dioxide.